Hello everyone, my name is Rongkun Xue. I'm from Xi'an Jiaotong University. Today, I'm very happy to share our work called Pretrained Reversible Generation as Unsupervised Visual Representation Learning. This project was completed during my internship at the Shanghai Artificial Intelligence Laboratory. If you are interested in our work, please feel free to scan the QR code below to learn more about the project and read our paper. Inspired by Richard Feynman's idea that what I cannot create, I do not understand, I start thinking about how creation can lead to understanding. In recent years, diffusion models have become increasingly popular in the community. However, most of the attention has become focused on how to generate images or videos faster and better. What is often overlooked is how to extract and understand the representation of ability inside diffusion models, and I believe this is something worth exploring further. Clearly, we can treat a diffusion model as a bridge or a mapping linking the original imager to a Gaussian noise space. What is special is this, unlike a VAE, which is trained with a reconstruction generation loss, a diffusion model is trained by adding noise to the data. If you think about it, then the train direction is the opposite of the generation. So here is the idea. If we build a reversible generation path, reversible is key. Then, when an imager is mapped back to a Gaussian state, can we treat that state as the better representation of the imager? On the left side of this slide, you can see how we build our diffusion. We designed three types of reversible model. First is score matching, second flow matching, and finally OT bridge matching. As pointed out in the SIT paper, we also believe that the first two are actually equivalent formulations. However, we made a somewhat disappointing discovery. Even a perfectly trained diffusion model only gives a very low classification score when mapping an imager back to its Gaussian representation. This is clear not good enough. To fix this, we applied the adjoint gradient method, which allows the imager itself to carry gradients for the measures. Once we did this, the representation ability of the model improved dramatically. At the bottom of the slide, you can see how, after fine-tuning, our model transaction from finally follow preserving all representations to selectively keeping the ones that help classification most. We went a step further to explore the mathematics behind this, and finally found the reason. As shown in the formula on the slide, our Pretrained actually provides a lower bound on the multiple information between the original imager and its optimal representation in the diffusion model. This part involves some autoencoder theory, so if you are interested, you can take a look at our paper for the detailed proof. Based on this, we can see that a reversible generation trajectory itself carries strong representational power, and when we joint fine-tune it with both generation and classification losses, every point along the trajectory becomes meaningful and surprisingly powerful. We have verified this through experiments on C4-10, TinyImageNet, and ImageNet, and the results strongly support our idea. Furthermore, when we integrated exciting generation model from the community, such as IT, into our framework, we also observed significant improvements. This shows that our approach can benefit from many exciting generative models, and that it doesn't rely on any special neural network architecture. In short, we believe our work takes a step forward in bridging generation and classification, and we really look forward to your discussion and feedback.